Okay, good afternoon. Are you ready? So today, today and tomorrow, sorry, Professor Mutlu cannot teach. He's giving talks into conferences, and he will be back next week. So today and tomorrow it will be me who will explain the two lectures. So what we have today is this lecture 9 about von Neumann model, the ISA, and we will talk about the ISA in the architecture in LC3 and in MIPS. Well, as you know, I'm Juan. I'm a postdoc with Professor Mutlu. Over the course of the lecture, please feel free to ask any questions or any clarifications as needed. So this is the agenda for today and for the next few lectures, for today and for tomorrow and for the next few lectures. So as I said, today we are going to cover the von Neumann model, which is, let's say, the most basic model of a computer, also the most popular. And we will see the LC3, or we'll start studying, learning the LC3 architecture as an example of a computer that follows the von Neumann model. But it's not the only one, so that's why we are also going to talk about MIPS. We won't talk about MIPS with such a level of detail, but we will also get familiar with the MIPS ISA, and of course the LC3 ISA. Tomorrow, we will continue with LC3 and with MIPS, and we will focus more on programming. And in the next lectures, starting next Thursday, Professor Mutlu will explain microprogramming, single cycle microarchitecture, and then the multi-cycle microarchitecture and microprogramming. So in this slide, you have the required readings for this week and for next week. For this week, it is essential to read chapters 4 and 5 in Path and Patel, where you will see, you will find the von Neumann model and the LC3 architecture. And it will also be very good to read chapter 6 in Harris and Harris, where the MIPS instruction set architecture is explained. You will also find very useful the appendices in Path and Patel, A and C, especially Appendix A for today's lecture and for tomorrow's lecture. And Appendix B in Harris and Harris, where you will find all the MIPS instructions. And also you can continue reading chapter 5 in Harris and Harris, and also the readings for next week. Next week are also in the slide for the microarchitecture and single cycle microarchitecture, multi-cycle microarchitecture, and microprogramming. Okay, so let's start with the contents that we need to visit today. What will we learn today? So as I said, what we are going to learn is the von Neumann model and LC3 as an example of von Neumann machine. And then when we give an overview of the von Neumann model, the LC3, and the instructions that can be executed in this machine and also in the MIPS machine, we will start talking more in detail about the instruction set architecture. As you will see, the instruction set architecture is not only the collection of instructions that can be executed in the computer or on the computer, but it's also details like what's the format or encoding of these instructions, or what are the addressing modes. I don't want to define the addressing modes now formally, but essentially this is the way that we are going to follow to access the operands of the instructions. Anyway, let's start with the von Neumann model. So, what you have learned in the previous lectures is combinational circuit and sequential circuits. So I think you already know that with these circuits, combinational and sequential, you can build decision elements, for example, a finite state machine, and you can build storage elements, for example, a memory or registers. So these are going to be the basic elements of a computer. Why do we need two computers? Because we want to run tasks on them. We want them to perform tasks for us, right? And if we want to get a task executed on a computer, what do we need? For sure, we need a computer, and that's why that's the first thing we are going to talk about, how to build a computer. We will need data that we are going to process, and we will need a program, which is the collection or the set of instructions or orders that we are going to give to the computer. An instruction is the smallest piece of work in a computer. So that's what we are going to talk today about. Computer, how to build a computer, or let's say the most basic design of a computer, and then the instructions that we will execute on this computer. So let's start building the computer. And if we want to build a computer, same as if we want to build a house, we need a plan, or if we want to manufacture a car, we need also a design. We need a model here to build a computer. And this model was proposed, the most popular, let's say, the dominant model over the last 70 years was proposed by John von Neumann in 1946. John von Neumann was studied here in ETH, and actually he studied chemistry, so it's very likely that he studied in CAB, which is the old chemistry building where the systems group that we belong to is located. In this report, preliminary discussion of the logical design of an electronic computing instrument, he proposed a model consisting of 5 parts. The memory, where we're going to store data and programs. The processing unit, where we are going to execute in an effective way these programs. The input, because we need to somehow feed the computer with information that is going to be processed, and the output, because the computer will return some results. So input and output are the way that we use to interface with computers, to communicate with them. And finally, we will need a control unit, because same as we have a brain, we need to have something in the computer that makes the decisions. So as I said in the beginning, throughout this lecture, we are going to consider 2 examples of the von Neumann model. One is LC3. You can find all the information about LC3 in Pat and Patel. And the other one is MIPS. You can find MIPS in Harris and Harris. And this is the von Neumann model. These are the 5 elements. Wait a second. These are the 5 elements that I mentioned. Let me see if I can use this. Okay. Seems like I can use it. This is the memory. In the memory, we have 2 important registers, the memory address register and memory data register. We will talk about them soon. We have the processing unit, where we have the ALU, where we really execute the operations, like, for example, an addition or a subtraction. And we will also have some temporary storage that is called the registers. We have the control unit with the program counter and the instruction registers, and input and output. As you can see, there are arrows connecting all these 5 elements. Some of the arrows are solid. When you see a solid arrow in this picture, this means that these are lines to send data or to move data from one element to the other. For example, from the memory to the processing unit, we need to move data, and from the processing unit to the memory, we will also have to move data. And then you see that there are also some dashed lines. And all the dashed lines are starting in the control unit, right? These dashed lines represent control lines. So they are going to be used by the control units to conduct the performance of all the computer, to give orders to all the elements in the computer. So let's start talking about the memory, and as you can see, and about these 2 registers, the memory address register and the memory data register. So why do we need a memory? Because we want to store data and we want to store programs. You already know that a memory contains bits because that's essentially what a computer understands, right? Computer only can process ones or zeros, and we have a way to represent any type of information as ones or zeros. So these bits are grouped, we'll see, we know that these bits are grouped into bytes. A byte is 8 bits, and they can also be grouped into words. The size of a word is something that we are going to define in each particular architecture. So for example, as you will see, in LC3, we use words of 16 bits, that is 2 bytes, and in MIPS, we use words of 32 bits, or 4 bytes. So another important thing is what is called the addressability. That is how the bits are accessed. When we want to access some piece of data from memory for reading or for writing this piece of data, we need to access, or we will access, a certain number of bits. So in case that the number of bits that we access is the word length, that is the collection of bits that we access is 1 word, we say that the computer is word addressable. Otherwise, we will say that it is, if what we access is a byte, we will say that it is byte addressable. So with one particular address, we are going to be able to access 1 word in a word addressable memory or 1 byte in a byte addressable memory. So, and the total number of addresses, which is more or less the total size of the memory, is the address space. This address space in LC3 is 2 to the 16th. So if we want to access 2 to the 16th different memory locations, we will need 16-bit addresses. In MIPS, the address space is 2 to the 32, so that's why we need 32-bit addresses. Okay, as I said, in order to access all these words or bytes, we need an address. For example, in a word addressable memory, each data word has a unique address. In MIPS, if we consider that MIPS can be can have a word addressable memory, we are going to have 1 unique address for each 32-bit data word. In LC3, we have 1 unique address for each 16-bit data word. And this is a toy example of MIPS memory, where you can see all these words, word 0, word 1, word 2, and word 3. You see that each of the words is composed by 8 hexadecimal digits, because it is 32 bits. And each of these words has a word address 0 for word 0, word address 1 for word 1, and so on. This is in the case of a word addressable memory. But the memory can also be byte addressable. And in the byte addressable memory, we have 1 unique address for each byte. Actually, MIPS is byte addressable. LC3 is not byte addressable, but there is a newer version of, LC3 is not byte addressable, but there is a newer version of LC3, that is LC3B, that is also a byte addressable. And in byte addressable memory, what we are going to have is something like this. Each of the words is composed, for example, in MIPS is composed by 4 bytes, and for each of the words, we have 1 word address again, but now observe that the distance between 2 consecutive word addresses is 4. Why is that? Because this is a byte addressable memory, and each of the bytes has its own address. Okay? Now there is 1 question here in word address, so in word 0. We know that these 4 bytes are address 0 to address 3. But which one is address 0 and which one is address 3? So is this 89 address 0 or address 3, or this EF. So the question is, how are these 4 bytes addressed? And this is called the Endianness. I don't know if you have ever heard about this. This comes from the book Gulliver's Travels. Maybe you have read it or you have watched the movie by Jonathan Swift. The thing is that in this book, little Endians broke their eggs on the little end of the egg, and big Endians broke their eggs on the big end of the egg. So the little Endian broke the egg here, the big Endian broke the egg here. So back in the 80s, someone decided that this was a good way to explain how the bytes were addressed in memory. So that's why we have these 2 types of memory, depending on the Endianness, the big Endian and the little Endian. So if the most significant byte is, so this byte, the leftmost one, is address 0, and the least significant byte in the word is address 3, then we will say that this is big Endian. If it's the other way around, that is, if the most significant byte is address 3, we will say that this is little Endian. Okay? So is this really important? Does this really matter? What do you think? Not really, right? It's just a convention. Same as in German or in Spanish, we write from left to right, and in other languages, like, for example, Persian, people write from right to left. So it's exactly the same. But the qualified answer would be something like this. It's not important because it's a convention, except in case that one big Endian system needs to share data with one little Endian system. In that case, they will have to take this issue into account. Okay, so let's continue with the memory. Now we are going to see how access memory. As I said in the beginning, there are 2 registers that we are going to use to access memory. One is the MIR and the other one is the MDR. And we are going to use them to access the memory in the 2 different ways that we can access memory. For reading or loading, which means that we are going to take some value from memory, or writing or storing. And by using these 2 registers, memory address register and memory data register, we are going to read or write. For reading, we need 2 steps. In the first step, we are going to load the MIR with the address. So we will put the address that we want to access in this MIR. In the second step, the data will be placed by the memory. The data in that address will be placed by the memory in the MDR. If we want to write, what we are going to do in some ways the opposite operation. In the step 1, we will load the address into the MIR, and also, because we want to write something, we need to put this data into the MDR. In step 2, we will activate one specific signal, or maybe several signals, that in summary will be something like a write enable. So we place the address, we place the data in the corresponding register, we activate this signal, and then the data is written into the memory. Okay, so we are done for now with the memory, and now let's continue with the processing unit. So the processing unit can potentially have many different functional units. Actually, current microprocessors have a variety of units that can be like integer unit, can be floating point units, or can be SIMD for vector processing, for vector processing operations. But of course, because we want to start from the beginning, we are going to start considering a simple ALU, an arithmetic logic unit. In this arithmetic logic unit, we are going to be able to execute different instructions. In LC3, the set of instructions that we have is not, the set of instructions that execute in the arithmetic logic unit, it's not very big. As you can see, it's only 3 instructions. In LC3 is add, and not. In LC3B, it's XOR also included. In MIPS, we have a few more. We have add, we have sub, which is subtraction, we have multiplication, we have and, nor. There are also some interesting instructions like this shifting instruction, shift left and shift right if we want to shift the bits of a specific word. And we also have other instructions like this SLT, set less than. This will be, as we will see tomorrow, this will be very useful when we want to program loops. So the ALU processes quantities that are referred to as words. You're already familiar with that term. And these words have a length. In LC3, this length is 16. In MIPS, this length is 32. Observe that there is something common in LC3 and in MIPS. The word length, that is the size of these operands that are going to be used by the ALU, is also the same size as the addresses. So in LC3, we use words of 16 bits for quantities and for addresses. In MIPS, the size is 32. And where are we going to store these quantities? We are going to store them in temporary storage that is called the registers. Why do we need registers? Because we already have a memory. Yeah, that's true, but accessing memory, as I think you already know, it's quite time-consuming. And in every computation, there are some temporary results. So we don't really want to go to memory to store temporary results. That's why using the registers is useful. For example, in this case, we want to calculate A plus B times C. The intermediate result of A plus B can be stored into a register and then used for the subsequent multiplication. So, as I said, we have the memory, but it is slow, although it's big. So that's why we want to use the registers. And as you will see also, we need a way of moving data from the memory to the registers and from the registers to memory. So we are going to use these registers to have fast access to the operands. And typically, one register, as we said before, contains one word. So the total and the collection of registers that the processing unit has is the register set or file. And in LC3, we will see that we have 8 general purpose registers. These general purpose registers are R0 to R7, so we will have a 3-bit identifier, 3-bit number to identify each of these 8 GPRs. The size is 16 bits. In MIPS, we have 32 registers, and the size of them is 32. What if we want to store some data, for example, double precision floating point that is 64 bits? Well, we will use 2 registers in case of MIPS, for example. So the MIPS register file has, as I said, 32 registers. These registers have each of them one number, 5 bits to identify the register, and each of the register has a specific use. Some of them are more general purpose, like for example, S0 to S7, or the temporary registers, T0 to T7 and T8, T9. But there are also some other registers that have a more specific purpose. For example, register 0 is a constant value 0. We cannot modify it. And there are also some registers like A0 to A3 or V0 to V1 that are used for functions. When in a program we want to call a procedure, we will need to pass some arguments and the procedure will return some results. So that's why we need these registers. And also, as you will see tomorrow, we need this RA, register 31, to store the return address for a function. Okay, this is all for now regarding the processing unit. Now let's briefly talk about the input and the output. As I said in the beginning, input and output is the way, is the interface, or are the interfaces that we're going to use to interact with the computers. They are called peripherals, and as you can guess, there are different peripherals like keyboard, mouse, scanner, disk that can be used for input, and others that can be used for output, like a monitor or display, printer, the disk as well, etc. In principle, in LC3, we only consider keyboard for input and monitor for output. That's all regarding input and output. And now, let's talk about the control unit. So in the control unit, as I said in the beginning, this is the conductor of the orchestra. It's like the brain in the computer, and it's the component that is going to take care of the correct execution of instructions, the step-by-step process of executing a program. As you saw in the previous slide, this control unit contains one register that is called the IR, the instruction register, and there is where we are going to store the instruction that is executed, that is being performing one particular moment. And we need another register that is the program counter or instruction pointer that is going to store the address of the next instruction to be processed. Over this presentation, we will mostly call it program counter because let's say that that is the most common way. But probably instruction pointer is a most appropriate way of calling it because it's actually a pointer because it contains an address. And actually that is the way they are calling it is called in Intel architectures. So including these three registers, you are already familiar with what is called the architectural state or the programmer visible architectural state of the computer. Okay, and as you see here, we have the memory where we store programs and data. We have registers, some general purpose registers, some other registers with a special purpose, like, for example, the instruction register. And then we also have the program counter that will tell us what's the next instruction to be executed. So we say that this architectural state is programmer visible because the programmer can modify it by using programs or by creating or writing programs or using instructions. So we finish here with, let's say, the generic explanation of the von Neumann model. And now we're going to start talking about a particular architecture that follows the von Neumann model. And this is the LC3 computer or the LC3 machine. This is what is called the data path of the LC3 machine, which essentially is the microarchitecture, where you can see all the components that are part of the, not all the components, because this is a simplified picture, because we are starting with it, a simplified picture of the LC3, but you can already find here several components that belong to the control unit, this pink area here. The blue part is the processing unit, and recall that in the processing unit we have the ALU and we have the register file. You can already find them here. Here we have a memory, and here we have input and output. So one thing that you can observe in this picture is that there are many arrows, and some of these arrows have the arrowhead is black, and in the others the arrowhead is non-filled. So for those that the arrowhead is non-filled or is white, you have to know that these control lines are control signals. Actually, if you see here in the control unit where we have the finite state machine, we have all these many arrows that start in the final state machine and will go to all the different components of the LC3. And then we have the black arrows that are for data. Here, you see the 16-bit addressable memory. This is the memory address register. This is the memory data registers. Recall that we need both to access memory. And here, this input is the keyboard. In the keyboard, we also have two important registers. One of them is for data. For example, there's this KBDR is where we are going to store one character that is input by the keyboard, and we also have another register that is for status information. And that's something similar to what we have for the monitor. We also have one register for data and another register for the status information. So here in the processing unit, you can see the ALU that has two inputs and one output. The two inputs, one of them for sure comes from the register file. The other typically comes from the register file as well, is this SR2, but it can also come from somewhere else. We will see later where it can come from. Here is the register file in LC3 with the 8 GPRs. This is the instruction register where we store the instruction that is being executed, the program counter, the final state machine, as I said before, generate the control signals. And some of these control signals, for example, the ALU operation, this ALUK, that indicates to the ALU which operation should be performed. And other control signals, for example, this gate ALU is to control this three-state buffer that we have here. Observe that there are several of these three-state buffers in the data path. And we need to control them because we don't want them to be always writing into the processor bus. What could happen if they all are writing continuously to the processor bus? We will have some kind of collision in the processor bus, right? So the machine wouldn't work correctly. Okay, so we will keep talking about all these elements, all these components. The very first thing that we have to talk about is about the program. And as I said, you already know, the program is going to be stored in memory, same as data. The way the computer is going to process the program is by fetching instructions from memory sequentially. Typically, the memory will access memory to fetch or read one instruction that will be stored in the instruction register, and then it will decode and execute the instruction, probably store some results in memory or in a register, and finally it will continue with the next instruction. And this, you see it's like 3, 4 steps. Actually, later we will see that there are 6 steps. These steps are executed one after the other, and when you reach to the end, you start from the beginning. So that's why we talk about instruction cycle. The address of the current instruction is in the program counter. When we start executing one instruction, you will see that we increment the instruction by 1 in the case of LC3 because it's a word addressable memory, by 4 in the case of a byte addressable memory as we have in MIPS. By the way, in MIPS, and this is something that you will have to recall when you work in your labs, when you write assembly code in your labs, the OS, the operating system, typically sets the PC when the program starts the execution. So the address where the programs are going to start is this one here, this 400,000. Let's take a look at the very first program that we are going to see how it's stored in memory. This is the MIPS assembly. A MIPS assembly is like the human readable representation of the instructions. We are going to talk about that very, very soon. But that's not exactly what the computer understands. What is what the computer understands? Ones and zeros, right? So that's why we need this machine code that is a translation of this assembly into ones and zeros. Here, these ones and zeros are presented as hexadecimal digits. So We have 4 instructions. These 4 instructions are stored in memory and in some specific part of the memory, starting in this address here. When the program starts the execution, the program counter points to this first instruction. When we start executing instructions, the program counter increments, right? Okay. So let's start talking about the instructions more in detail. The instruction is the most basic unit of computer processing. Instructions are like the words in the computer, in the language of the computer, and the ISA is the vocabulary. The language of the computer can be written, and as you have seen in the previous slide, in machine language, that is ones and zeros, what the computer understands, or in the assembly language, because, I mean, talking about all these instructions like 110010 is going to be really tough, right? So that's why we need something that is more human understandable or human readable. We are going to learn LC3 instructions and MIPS instructions, and we're going to start with some examples. Among these examples, you will see the 3 types of instructions that we need in the computer to write programs. We need operate instructions to execute operations in the ALU. We need data movement instructions to read from and write to memory. And we will need control flow instructions in case we want to change the flow of execution, because until now you have seen that the program counter is incremented by 1 or by 4, depending on the memory. But at some point, it will be good to, for example, be able to do a jump and go to some different part of the program and of the memory. So let's start with one operating instruction, addition. You are already familiar with high-level language code, and this could be, for example, C, A equal B plus C. How is this represented in an assembly? This is kind of generic assembly. This could be something like this. Add, it's a mnemonic to indicate what is the instruction. And then you see that we have 3 operands. 2 of these operands are the source operands, B and C. The third one is A, which is the destination operand. And here you see the semantics of this operation. What are the semantics? What the instruction performs. And what this instruction performs is the addition of B plus C and stores the results in A. This is kind of, as I said, like kind of generic representation of an addition in assembly language. Let's go to the particular representation for LC3 and MIPS. In LC3 and in MIPS, we are going to use registers to store these variables, A, B, and C. For example, we could use R1, R2, and R0 in LC3, or S1, S2, and S0 in MIPS. In LC3, the addition, and this is already, let's say, real assembly, is the LC3 assembly. We have the addition with our source operands, R1 and R2, and our destination operand, which is R0. This is going to be represented as machine code, right? As ones or zeros, that's what the computer understands. So we need a way of representing all these 4 elements that you can see in the assembly, the mnemonic and the operands. So that's why we need this, what is called instruction format or encoding. As you can see, we have some bits here, 4 bits to represent the operation. So this is what is called the opcode, the operation code. Here we have some 3 bits for the destination registers, 3 bits for the source register 1, and 3 bits for the source register 2. Sometimes you will see, and actually you have seen that before, that we will use the hexadecimal representation for these bits to be more brief. So this is the opcode, 4 bits. The opcode will be different for each of the instructions, for each of the operate instructions. For example, for add, the opcode is 0001. For AND is 0101. And then we have here the source registers and the destination register. And here you can see the semantics for the add operation and for the AND operation. So this is the instruction format or encoding in LC3 for operate instructions. What about MIPS? It's very similar, as you will see. This is the MIPS assembly. Here, the destination is S0, the operands, the source registers are S1 and S2. And this is how we are going to represent them in the machine code, or these are the field values, like in hexadecimal, in decimal numbering, and this is in the binary representation. Why do we have here 17, 18, 16? Because this is a number that identifies each of these registers. S0 is the register 16, R1 and R2 are, S1 and S2 are registers 17 and 18. So let's take a closer look at this instruction format for the addition in MIPS. It's something like this. We, again, have an opcode, but observe that in this instruction, the opcode is equal 0. And that is because we have one funct, this funct field, this least significant 6 bits that represent the operation in R-type instructions. R-type instructions are all instructions that use this instruction format in MIPS. This is called R-type in MIPS. Why is it called R-type? Probably because it uses registers as operands, right? So the last thing here is that we also have this shunt bit. This means shift amount. It's going to be used for the shifting instructions that I mentioned before. We can talk about this later again. Okay, that was an example, or one example in, that was an example in MIPS and in LC3 of operate instruction. Now we're going to see an example of data movement instruction because we need to access data from memory. So we are going to see next one instruction in each of the 2 assembly languages and in each of the 2 ISAs for reading or loading from memory. Writing or storing is very similar. We are not going to talk about that right now, but we will see it later. So load word, this is reading from memory, right? In high-level language code, you access one specific memory location by doing something like this, A equal AI. So how is this going to be in our generic assembly? Is something like this, load A, which is the destination, and capital A and I, which are going to be used to address the memory. So we have the mnemonic, we have the base address, which is like the pointer to an array in high-level code, and we have an offset, which is the index in a high-level code. And then we have the destination operand. These are the semantics, essentially the same as we have in the high-level code. So let's see how this is represented in LC3 assembly. In LC3, the instruction, for now, the instruction that we are going to use is called LDR. LDR comes from load register because here the base address where we are going to store like the pointer to the array is in one register, in this case R0. And then we have the index, which is these 2, that is called an offset. This is the semantics of this assembly instruction. And for MIPS, it's something very similar, and actually the semantic is exactly the same. These 2 are equivalent, LDR in LC3 and LW in MIPS. And the way we access memory in these 2 instructions is called the addressing mode. What's the addressing mode? The way we address memory, the way we calculate the address, and this addressing mode here is base plus offset. The base is stored in the register. The offset, as you will see, is stored in the instruction, but we will see that later. That was for a word addressable memory, but recall that MIPS is actually byte addressable. So if we want to access this element 2, we will have to multiply this word address by the number of bytes per word. That's why you see here this 8. So 4 bytes per word in MIPS. In LC3B, we have 2 bytes per word. Let me show you a couple more of slides, and then we will have the break. Let's quickly go through the encoding or the instruction format for this instruction for LDR or for LW. This is the instruction format for LDR. You see the opcode. In this case, the opcode is 6. The destination register is 3. There is where we are going to store the value that we read from memory. And these are the 2 elements that we need to calculate the address: the base register, R0, and the offset, which is represented in 6 bits. These 6 bits of the address, of the instruction, sorry. Something similar is what we have in LW. For LW, obviously the operation code is different because it's a different ISA. This is called the I-type format in MIPS. Okay, so yeah, I think we can have our break here, 15 minutes, and we will continue afterwards. Okay, let's continue. So we have seen how to execute the instructions, or what's the, how these operate instructions look. We have seen the addition instruction. We have also seen how the instructions that we need to read from memory, like this LDR or LW in MIPS look like as well. And now we are going to talk about how are these instructions executed, and we are going to approach a little bit to the data path and how the instructions are executed in the data path. So let's say that because we already know some instructions, we can speak the language of the computer. Now we need to figure out how these operate instructions, or how these memory data movement instructions are executed in memory. This is what we call, in the computer. So this is what we call the instruction cycle. I already mentioned the instruction cycle before. Now let me show you that this instruction cycle, in the LC3 architecture at least, has 6 steps or 6 phases. These are the fetch, the decode, the evaluate address phase, the fetch operands, the execute, and the store result phase. For example, what are we going to do in the fetch state, in the fetch phase? We're going to go to memory, and we're going to fetch the instruction that we're going to execute next. We need to decode this instruction, that is reading the operation code and know what exactly we want to execute, or this instruction wants to execute on the processor. In some cases, we will have to evaluate the address. For example, the LDR that we have just seen, we need to calculate the address that we will access in memory to read some operand that we will need later for computation. So in LDR, we need this evaluate address phase. We also, in some other cases, might need to fetch operands. For example, in the addition, we need to fetch 2 operands that are the 2 registers that we are going to add. And then, for sure, execute the operation in the ALU, and finally store the result. In some cases, we will store the result in a register. In other cases, we will store the result in memory. We will see some examples of this. Not all instructions have the 6 phases. For example, LDR does not require execute because LDR doesn't use the ALU. Add does not require evaluate address because add doesn't access the memory. But there are some other cases. For example, here you have this Intel x86 instruction, add EAX, EDX, that has the 6 phases, because here it has 2 operands. It has EDX, which is a register, and then it has this EAX, which is a register that contains an address that should be accessed in memory. So this instruction accesses memory, takes one register, and adds both. So that's why it needs the 6 stages, or 6 phases. This is what is called the instruction cycle, because we have this cycle. When we finish the store result phase for one instruction, we have to start and go, we have to restart and go again to the fetch phase for the next instruction. So let's start talking a little bit more about each of them. Fetch is the stage or the phase in which we are going to access memory to read one instruction and store the instruction in the instruction register. This is common for every type of instruction. There is no difference between the data movement, operate, or control instructions. The complete description, it has 3 steps. In the first step, we move the contents of the program counter to the MIR, because we are going to access memory. The MIR contains, recall, that contains the, or has to contain the address that we want to access in memory. And at the same time, we can increment the PC so that the PC starts pointing to the next instruction in the sequence. And then we have to interrogate memory. We have to ask the memory if it has some data for us in the address that we have stored in the MIR. And the memory will move that data from the data element from the specific memory location to the MDR. And in the third step, we will move the instruction that we have just accessed from memory from the MDR to the IR, to the instruction register. Let's take a closer look here on the data path. In the first step, we, as you see, we move this PC to the MIR, and we also increment the PC. In the second step, we read from memory and store the instruction in the MDR, and in the third step, we load the IR with the contents of the MDR. So now we have our instruction in the IR. And next, we will decode it. That's something that the control unit will do. How the control unit decodes the instruction is something that you can already figure out. It uses a decoder. You're already familiar with the decoder. You saw it in lecture 6. And in this case, in LC3, we need a 4 to 16 decoder because we have 4 bits that represent the operation code, and we can have up to 16 different instructions. So this operation code is the most significant bits of the instructions. So this is the most significant, these are the most significant bits of the IR, are bits 15 to 12. And the remaining 12 bits will be, might have different use depending on the instruction, but that's something you have already seen if you compare add with load word, and you will see more details about this next. So how is this decode stage executed on the LC3 datapath? Decode identifies the instruction. So the finite state machine is fed with the 4 most significant bits of the IR. And afterwards, it will generate the control signals that we need to control to handle the operation in all the data path components. So next, the evaluate address. This phase is necessary in LDR because we need to calculate one address. So it's going to be used to compute the address of the data word that is going to be accessed in memory. Recall that in load word, what we do is taking one register as the base address, and then we add some offset. This gives us an effective address that contains in memory the element that we want to read and store in a register. So in this stage, what we do is calculating the evaluate address. As I said before, this is not necessary in add. So let's take a look at how we do this on the data path. For LDR, calculate the address, adding a register and an immediate. This might be different in other instructions, but because LDR is like the first instruction that we know to access memory, let's take a look at how it is done. We have the offset in the lower part of the instruction register. We have one register in the register file that is used as a base, and we are going to add them both, and we will later put the result in the processor bus because we will need to bring this address to the MIR. Observe that here, we have drawn here like this additional other. We could use potentially the ALU, but in LC3, there is a specific other to calculate this addition between the base register and the offset in the instruction. So next is the fetch operands, and we can have fetch operand stage in LDR and also in add, but the operands that we are going to fetch are different. So in the case of LDR, what do? What we do is reading from memory. We load the MAR with the result that we calculated before, with the address that we just calculated in the previous phase, and then we read memory, so the operand will be placed into the MDR. Here it is called source operand because it's the result that is stored, it will be later stored in a destination register and will be for sure a source operand in later operations, later instructions. In case of the addition, what we do in this fetch operand phase is accessing the operands from the register file. Depending on the architecture, we can do this fetch operands phase for addition simultaneously with other phases. For example, in some current microprocessors, in MIPS, for example, it's like this. This phase, this fetch operand phase for the addition instruction can be done at the same time that the instruction is decoded. So there are different ways of optimizing the data path, but let's say the basic functionality that is represented by these 6 stages or these 6 phases exists in every microprocessor. So let's see how we fetch the operands for LDR on the data path. First, we load the MIR with the address that we calculated before, and then we read from memory and store the value that we read in the MDR. The execute, it's very simple for now because it's only in addition or other operate instructions. In the case of addition, it performs the addition in the ALU. It uses these 2 source registers. It uses the ALU and produces some result. And finally, the last stage is the store result, where we write the result in the designated destination. Depending on the instruction, the designated destination might be a register, like in the case of the addition or the load word instruction, or it could be memory, right? If we were executing a store operation, a store instruction. So for example, in LDR, we move the value that we just obtained from memory from the MDR to the register file. Where are we going to store it? We are going to store in the destination register, whose bits, the bits that identify it are fed through this input. Any questions so far? Okay, so if you don't have any questions, let's continue. Again, this is the instruction cycle, the 6 stages, and when we finish the last stage or the last phase, we start from the beginning. And now let's take a look at how we can change the sequence of execution, because the only thing that we have considered until now is that every time an instruction is executed, the program counter is incremented by 1 in LC3, by 4 in MIPS, but this essentially means that the program counter goes to the next instruction in memory. So if we always do it this way, we can only execute programs in a sequential manner, in program order. So at some point, we might need to change the sequence of execution. I think I mentioned in the beginning that we might need to do this if we want to call functions or subroutines that might be stored in a different part in memory. So we will need to change the program counter to point to the address where the function or the subroutine starts. So we have some specific instructions for that. Those are the control instructions. And these control instructions allow us to run the program out of sequence. They change the program counter, and well, this wipes out the incremented PC, because the PC is always incremented in the phase stage, in the fetch phase. So one of the instructions that we can use to change this sequence of execution is called the jump, or unconditional branch. In LC3, this instruction is called JMP, and it has this kind of format. This is the opcode 1100, and it has one base register. This base register, in this example, is register 2, contains the address where we want to jump. For example, the address where the function starts. So this is our base register. This is the semantics. We store, what we do here is that we store the contents of R2, which will be a memory address, into the program counter. This is called the register addressing mode, because the way we are accessing the operand here is by simply accessing a register, which is the base register, R2 in the example. And then we also have some variations. For example, RET, that means return. This is a special case of jump where the base register is R7. We are going to use this RET, or this return instruction, when we want to return from an subroutine. So think about a program, you're executing your program, and at some point you want to call a function that is called add array or reduce array or something like that. So you will jump to another part in memory, you change the value of the program counter, you jump to another part in memory, you execute this reduce array or whatever the function or the subroutine is, and when it finishes, it executes this return instruction that brings you back to the place where you call the function. And actually, the place where you call the function is not exactly the jump instruction, but the next instruction. So this R7 is going to store the return address. Okay, another variation is JSR or JSRR, which actually are the ones that we use to jump to the subroutine. Jump instruction, as you will see tomorrow, is more useful for writing loops or like while loops or for loops. For the specific jump to subroutines, we have this one, same as you will see that we also have the specific one in MIPS. So in MIPS, what's the jump instruction is J. And it is interesting because here, it's not exactly the same as in LC3. Here we use this J-type format in which most of the encoding are these 26 bits that are called the target. And what's that? That's exactly, well, not exactly, but it's more or less, as you will see, the address to which we want to jump. It's kind of immediate address that we have in the instruction. So the opcode for jump for J is 2, target, and here you see the semantics. What we're going to store in the program counter is the target, but observe that the target is only 26 bits. And what's the size of our addresses? What's the size of the program counter in MIPS? It's 32, right? So we need somehow to extend from 26 to 32. The first thing we are going to do with these 26 bits is shifting them 2 positions to the left. That's why you see this multiply by 4, because you know that multiplying by 4 is the same as shifting 2 bits to the left. Why can't we do that? Because MIPS is byte addressable. And what we want to access is one word of 4 bytes. So we don't really need we don't really need to store these 2 least significant bits of the address. These least significant bits are could be used to identify 1 byte, but here, because we are accessing an entire word, these 2 bits will be 0, 0. So that's why we don't need to store them here in the instruction. So now we already have 26 plus 2. We have an address with 28 bits, but still we need 4 more bits, right? Where are we going to take these 4 more bits from? We are going to take the 4 most significant bits of the current PC. Actually, it's not the current PC, it's the incremented PC. Why is that? Anyone can tell me? The jump instruction is in a specific address in memory. Every time we fetch one instruction, we increment the PC, right? So in the fetch phase, we have already incremented the PC. So the PC is pointing to the instruction that is in memory after the jump instruction. So that's why this footnote here says that this is the incremented PC. This way of accessing the operand, in this case the target address, is called the pseudo-direct addressing mode in MIPS. There are some variations. I mentioned before that we have a specific jump to go to a subroutine. This is called jump and link. And we also have a specific jump to return from the subroutine. This is the jump register. And actually, if you compare this jump register to the jump that we have in LC3, you will see that it's exactly the same. It has the same semantics. This one also uses the register addressing mode. Okay, this is the LC3 Datapath. Again, I just want to show you a few more components, for example, because you need them to understand the next slide. For example, here, we have this 3-step buffer that is controlled by one control signal that is called gate PC. If we activate this gate PC, we will write the content of the PC to the processor bus. We need that to access the instruction, right? We also have this ld.mir. This is load memory address register. We will activate it when we want to really write something into or load something into the memory address register. We also have this PC multiplexer. The PC multiplexer is used to choose among different possible values for the PC. By default, we will be choosing this input that is the incremented PC. You see here the +1, but for jumps, we might need to choose a different one, as we have seen in the previous slides. We also have one gate MDR when we want to move the content of the MDR to the processor bus, and this LD.IR. Okay, so let's take the very first look at the finite state machine, because this is the finite state machine. This is the part of the computer that is going to take care of the control of the instruction cycle. And it has the different phases. You see here the fetch phase, the decode phase, and here these states here represent the rest of phases. And some of these phases have one state, some of them might have more than one state. For example, in the final state machine, for example, fetch has these 3, state 1 to state 3. Let's start with state 1. What is the very first thing that we are going to do in the fetch phase? What we are going to do is, the first thing we want to do in the fetch phase is accessing memory to read the instruction, right? So what we have to do is moving the program counter to the memory address register. In order to do that, we need to assert some of the control lines that you have seen in the previous slide, like gate PC and LD.MIR. We activate gate PC to put the content of the PC into the processor bus, and then or at the same time, we activate the load MIR signal to allow the processor bus to put that memory address into the MIR. At the same time, we can increment the PC. So you see that we increment the PC and we select in the PC multiplexer the corresponding input to update the program counter. In the second state, we are going to read memory. So the MDR will be loaded with the instruction. And next, we will move the content of the MDR to the instruction register. In order to do that, we have to assert, or the final state machine has to assert the gate MDR and the load IR signals. Depending on the instruction, depending on the opcode of the instruction, we might go to some of these different states that come next. So, for example, if the instruction is jump, we will go to this state here that will finish in this state 63. And what do we do in this state 63? We load the register that is the base register that is indicated in the jump instruction. We load the contents of this register into the PC, because the content of this register is the address where we want to jump. Okay, you will see the full state diagram later, but if you want to take a look, you can go to the Appendix C in Pat and Patel. Okay, so we are done with these basics of the von Neumann model and for the LC3 computer. Also, we have seen already seen some details from the MIPS machine. Now we are going to talk a little bit more about LC3 and MIPS instruction set architectures. The instruction set architecture, if I'm not wrong, this is something that Professor Mutlu has already defined, is the the interface between software and hardware. So it's something that we have between the programs, the high-level language programs that programmers or compilers can generate between the programs and the microarchitecture. So the ISA specifies the memory organization. We have already talked about this. Also specifies the register set. We have already talked about this as well in LC3 and in MIPS. And it defines the instruction set, which is the collection of instructions that we can execute on the microarchitecture, including different operation codes, including different data types, and including different addressing modes. So for the instruction set architecture, So the instruction set, as I said, defines opcodes, data types, and addressing modes. We have already seen our first examples, addition and LDR in MIPS, and also, in LC3 and also in MIPS. Regarding the addressing mode, I think we have already mentioned some in the previous slides. Register mode is one possible addressing mode. Base plus offset is another possible addressing mode where we use this base register and we add some offset. And regarding the opcodes, that's, let's say, the set of opcodes, the total number of opcodes that we have is the total number of instructions that we will have, right? How many instructions do we want to have in our ISA? Do we want only a few or do we want many? That depends. I mean, there are always trade-offs here. For example, in the architectures that we are going to, or we are studying in detail, like LC3, the total number of opcodes is very reduced, especially in LC3, right? Where we have 4 bits for the opcodes, so the total number of opcodes that we can have is 16. We can have up to 16 instructions, but there are some more complex or many, instructions or architectures that are much more complex and can include many more instructions. Those are called the CISC instruction sets. We might go into these details about this kind of instruction sets later. But here you just see some examples. For example, the HP precision architecture, which has an instruction for this operation, multiply, add. In x86, we have multimedia instructions. For sure, you might have heard about MMX or SSC instructions that are vector processing instructions, or even in BIX, there was a opcode to save all the information of a program prior to switching to another program. So it's really a very complex instruction. There are always trade-offs here, and those trade-offs are related to the hardware complexity and the software complexity. So if our instruction set has very small number of instructions, we will probably have programs that have many more instructions, because in order to execute the same operation, we will have to do many more of these, we will have to execute many more of these simple instructions. But the good thing is that the hardware complexity will be much smaller. The hardware, the microarchitecture that we need to execute those instructions will be much simpler. LC3 is an example of that. Where is the burden in that case? The burden is probably on the compiler or the programmer, that you need to write or generate programs that are much longer. It could be the other way around. You could have instructions that are very, very complex. This will give you programs that are much, much shorter, but the hardware will be, for sure, much more complex. The good thing of using, let's say, a reduced set of instructions, the good thing of using only a very few instructions is that the hardware is simpler, and this way it can work faster. So you can have faster machines. Okay. We're going to see that there are, actually something that we have already mentioned, there are 3 types of operations, 3 types of opcodes. They identify operate, data movement, and control instructions. These are the opcodes in LC3. I mean, these are the instruction in LC3, the instruction encodings in LC3. And as you already know, the 4 most significant bits are the opcode. as you see, all of them except one identify one instruction. You will see here addition, and jump, etc. And there are also some reserved encoding. This is not really used, in which case we might need to use this reserved encoding in case that we want to extend the instruction set. That could happen and could be a good idea because maybe the users need one extra functionality or something like that. So we could generate or we could create new instructions. So that's why it's good to have these reserved encodings. This is for L3B. As I mentioned before, this is like a newer version of LC3. There are some, not many, but some differences. For example, here the JSR and the JSRR instructions are merged. They now share the same encoding. We have an instruction that is the XOR. You know that this one is also very useful in today's computing systems. And we have also one extra reserved encoding. And here you can see the operation codes or the function codes for R-type instructions in MIPS. Actually, for all R-type instructions in MIPS, the opcode is 0, and is this field funct that determines what's the operation to execute. So that's the field that distinguishes between the different instructions. You can see some of them. You're already familiar with JR, for example, it's here, or even this shift left logical or shift right logical that I mentioned in the beginning of the lecture. And here you can see a few more. For example, add or sub or XOR, etc. So regarding the data types, we can also have, same as we can have more or less complex sets of instructions, we can also have ISAs that support more or less number of data types. In LC3, we only consider 2's complement integers. In MIPS, we can have 2's complement integers, or we can have unsigned integers, or even floating points data types. But there are, again, trade-offs here. What's the trade-off of having more or high-level data types in the ISA, and what are the disadvantages? This is related to what I mentioned before. If the variety of data types that your ISA has is bigger, you can be closer to the high-level program. That's what is called the semantic level. So your semantic gap will be smaller. If this is the level where your high-level language is, and this is where your ISA is, the semantic gap is small. This means that, I mean, in the case of the data types, this means that you have many different data types that can be directly used by the compiler or by the programmer when going from the high-level language to the ISA. If the semantic level of the ISA is smaller, is lower, if you have very few data types, then the semantic gap will be longer. But again, it's a matter of trade-off between the effort that the compiler or the programmer has to do and the effort that the microarchitecture or the microarchitecture designer has to do. Okay, here you can see two examples. For example, early RISC architectures only had integer type, like MIPS, for example. Floating point was included in MIPS later. And in other architectures like this, Intel 432, you could even find object data types, similar to the objects that you use in object-oriented programming. So regarding the addressing modes, this is the way, the mechanism that we use to specify where the operand is located. We have already discussed some of these. In LC3, there are 5 addressing modes. We have the immediate or literal, when we find the operand in the same instruction. It is called immediate because we can access it immediately, or literal because we can say that the operand is literally in the instruction. The second possibility is the register. You're also familiar with the register mode when the operand is stored in a register. And then we have 3 memory addressing modes in MIPS, in LC3. One of them is PC relative, the other one is indirect, and the third one is base plus offset. You are already familiar with base plus offset because this is the one that is using LDR. In MIPS, we have some of these. We don't have the indirect addressing mode, but we have the pseudo direct addressing mode that we mentioned when we saw the jump, the J instruction. Okay, so let's start with the operate. Let's start with some operate instructions. We are already familiar with add. Actually, we are also familiar with and as well. Now we are going to talk about the third one, because in LC3, recall that there are only 3, add, and the third one is not. Not is said to be a unary operation. It's called unary because it only uses one source operand. That's the way the not operation works, right? You just need one register, and not simply means flipping the bits, applying the bitwise not. Add and AND, that we have already discussed before, are binary operations because they have 2 source operands. In case of add, it's addition, 2's complement addition. In case of AND, it's bitwise AND. And in MIPS, we have many more instructions. Actually, if you have seen previously in the table that you have like 2 or 3 slides ago. And all of them are, these all air types are binary operations. And we also have the immediate versions of these air types. They use a different format in MIPS. They use the I-type format. We will see some of them later. So let's start. F-type is the the last type of operations. Probably we won't go into much detail with floating point operations, but you can find them in chapter 6 in Harris and Harris. Okay, so let's start talking about NOT in LC3. This is the assembly code for NOT. We have one source register that in this case is register 5. We have one destination register, in this case is register 3, and this is the machine code for this NOT operation. And here, in this part, in this picture in the right, what you can see is the relevant data path for the NOT operation. We need the register file to execute the NOT operation. We need the register file where we will find one source register. This source register is fed to the ALU, and this ALU will be steered by some bits coming from the final state machine. The ALU executes the NOT operation, and the result is stored into the destination register. Okay, it's clear, right? So that's LC3. What about MIPS? We don't have unary operations in MIPS, so we don't have NOT. How could we execute NOT in MIPS? Any idea? So it's something similar to what you can do when you generate. So you have the answer? You could use an AND. If I'm not wrong, I think MIPS doesn't have an AND, but you could use NOR with exactly the same purpose. That's correct. Very good. Okay, so this is regarding NOT. We are going to see next some more operate instructions. I think we are about to finish, but let me give you an overview of what is coming next. So for these operate instructions, we are going to see how add immediate, for example, is executed in the data path. And also, we are going to discuss how subtraction can be implemented in LC3 and also in MIPS. So for the instruction, I'm going to finish with these operating instructions with one literal, and then we will finish until tomorrow. So let me show you how these operating instructions with one literal are in LC3. For AND and for add, we have the same operation code that we have for the versions that use the source operand. The registers are source operand, but here the difference is that we use this immediate. So as you can see in the semantics, one of the inputs is one source register, the other input is the immediate. We will talk tomorrow about how this sign extension is performed. So this is regarding LC3. In MIPS, we have a similar way of expressing this with the I type, but I will show you that tomorrow. Thank you very much for your attention, and enjoy the evening.